session. Our first speaker is Professor Dawei Chen of Boston College. He will talk about geometry and dynamics on flat surfaces. Please welcome.
I'd like to thank the organizer for inviting me. It's a great pleasure for me to attend the ICBS and stay at Binsa to meet many old and new friends. And thank you also for coming to my talk. And during my talk, so if you have any questions, just feel free to ask me. So the first half of the talk, I'll give an introduction to this topic. So a flat surface in my talk refers to a polygon in the Euclidean plane that satisfies certain edge identification procedure. So I want to identify the edges of this polygon in pair. So where two edges in each pair are identified by translation. So there are parallel edges, like the same vector in the Euclidean plane, and I glue them by translation. I'll show you some pictures soon. And secondly, I require, after this edge identification, some vertices of the polygon will become the same point. If you count the angle at a point, sometimes the angle can be bigger than 2 pi. Then I require this angle must be an integer multiple of 2 pi. It can be 2 pi, 4 pi, 6 pi, and so on. And if the angle at a special point, after identifying several vertices together, if the angle becomes bigger than 2 pi, like 4 pi, 6 pi, 8 pi, so on, then we call it a saddle point or a cone point. So in particular, at such a special point, if the angle is bigger than 2 pi, it cannot be flat. It must be a conical singularity under the nearby flat metric. And we also call it saddle point, like a saddle point. So here's a local picture around the saddle point of angle k times 2 pi. So we can form the neighborhood of such a cone point or saddle point by taking k flat disks that are decomposed into 2k pairs of half disks. And we can identify the edges in the following way. Say I identify this B1 with the lower B1, just glue, and I turn, say, counterclockwise to A2. Then this A2 glues to the next edge A2 and turns again to B2, and B2 glues with this B2 and go on until you reach the last disk. You go back to A1, and A1 glues back to the first A1. So altogether, you can check the blue points, the centers of these K disks, will be identified as the same point. So in particular, this blue point, after identifying the centers of disks, actually become one point with angle 2 pi times k, because we are using k disks to glue them together. Okay, and the flat metric is naturally induced by using the flat metric on a standard disk. So you can also think of this procedure locally as a ramified cover of degree k over one disk. So you can pull back the metric from the standard disk to the gluing of the k disks, where at the center you get extraneous angle. That's the local behavior of a cone point in a flat surface. So what about some global picture, global examples? So before I say it, so let me also give you another equivalent viewpoint, which might be a little surprising to some of you if you have never seen this correspondence before. So equivalently, the kind of flat surfaces I introduced, they can also be explained by using holomorphic differential one form called omega on a compact Riemann surface, denoted by X in this talk. So if you have so here I consider this omega, I always consider it to be not identically zero. So if this surface X is compact, a non-trivial holomorphic differential one form can only have finite many zeros. They're isolated. So if you first consider generally away from the zeros of the differential omega, you can find some suitable local coordinate denoted by Z here. So if omega is not zero locally, I can find a suitable holomorphic local coordinate denoted by z, and to represent this differential one form omega just as d of z. And now you can think of this z comes from the standard Euclidean complex coordinate in the Euclidean plane, and then that naturally induces flat metric or Euclidean metric by using the xy horizontal and vertical coordinates of z. And if you have a special zero of this one form omega, where the zero order is given by some positive integer m, then you can also choose a local coordinate denoted by w here to write this different form omega as w raised to the mth power times dw. And if you think about this, you can rewrite it up to a non-zero scaling as d of, as a derivative of d of w raised to n, the power of n plus 1. You differentiate, you'll get w to the mth dw up to a constant. That tells us if you have a zero of order m, so you don't just get dz, but you get a higher power of your local coordinate. That means if you compare with a nearby non-zero flat metric, so at this 0 point of omega, you will have m plus 1 many flat disks glued together, like in the last picture. Sorry, going in the wrong direction here. You have m plus 1 disks glued together to form a special point. Yeah. So in this case, that tells us if you have m plus 1 disks glued together to form a special point as a center, that center point will have angle given by 2 pi times m plus 1. So let's look at some global examples. So let's consider the first case of genus 1, a flat torus. So here, I can take like a parallelogram with two pairs of parallel edges. So let's first identify the top and bottom horizontal edges. So you can wrap it up to get a cylinder like this. And we can also identify the left and the right, the two vertical edges. So that becomes the two circles on the left and right. If you imagine you close this up, you actually get an everywhere flat torus. In other words, if you stand on the torus just locally, you cannot recognize you're actually on the torus because locally it is flat. It's like a regular point in the flat torus. Even if you sit on the edges or even at the vertex, after gluing, even the vertex looks like a regular point because the angle, if you add up, will exactly be 2 pi. So it is everywhere flat. But that also coincides with our intuition, no matter what background you have on a genus 1 torus or genus 1 curve. So you have a nowhere vanishing holomorphic differential. So it is, you know, for such a differential, there's no zero. So it is everywhere flat. Everywhere you can write it as dz, so there's no special point. However, if you go to higher genus, so let's look at another example. So this picture might be new to some of you. So I take an octagon with 8 edges that decompose into 4 pairs of parallel edges labeled by the same vi and vi. So for example, I glue v1 and the other copy of v1 by translation. In other words, I have some local coordinates here. And maybe here I have z1, here I have z2, then z1, z2. They differ by translation, just according to the translate from the first copy v1 to the second copy v1. And you do the same thing for the other v2, v2, v3, v3, v4, v4. So you do have your local complex coordinates coming from the underlying chart in the Euclidean plane. And if you identify this way, let's check what happened to the vertices. If I take the lower left vertex of v1, it will be identified with the other lower left vertex of v1, so these 2 points become the same. And now I view this as the upper right endpoint of v2, and this point and the other upper endpoint of v2 becomes the same. And then I view this as the left endpoint of v3, this and the other left endpoint of V3 becomes the same. You continue this pattern, you'll see all the 8 vertices become the same point. That's why I label them all by the same color. And now you count the angles. We have an octagon, 8 edges that can decompose into 6 triangles, so the total angle is 6 pi. So it is an integer multiple of 2 pi, although it's higher than 2 pi. And if you wrap up this polygon, you get a topologically or real-oriented closed surface. We can compute the genus of the surface by using, for example, topological Euler characteristic. So we have, on the one hand, 2 minus 2g, where g is a genus, is equal to, we actually have a cell decomposition with how many zero-dimensional cells. It looks like I have 8 points, but after gluing, they all become the same point. So V0 actually is 1, one vertex. And for edges, originally we had 8 edges, but they actually grew into 4 different edges, one-dimensional cells, just labeled by V1 to V4. So I subtract the number of 1 cells 4. And the interior of the polygon is just 1 face plus 1. So this tells us the genus of this surface actually is 2. So it's an easy computation. And there's only one special point where the metric is not flat. That is at the vertices. After gluing, the special point actually gives us a double zero for the corresponding differential form omega. And how do we read off this differential form omega? Well, in the interior of the polygon, I can just think of omega as dz, right? In the interior, by taking z from the underlying Euclidean plane. Even if we have 2 different local charts, for example, I have V1 here, say V1, V1, I have a chart here by Z1, have another chart here by Z2. After gluing, they become the same points, right? So I have 2 different local current charts for the same point on the surface. So if I have Z2 equal to Z1 plus a constant as a transition function, so this is called translation, right? Because I glue V1 to the other V1 by translation. So this Z1, Z2, they are not globally defined coordinates on the surface. However, if I consider their derivatives, the differential form becomes globally defined. dz2 is equal to dz1. Because the constant, if you differentiate, is gone. So that tells us this omega is a globally defined object on the surface. And since it's a surface genus 2, again, depending on your background, if you know Gauss-Bonnet, or if you take the degree of the cotangent bundle of this complex aerial curve, you know any non-trivial holomorphic differential form should have 2d minus 2, which is 2 zeros counting with multiplicity. So here we only have 1 special point, so it must be a double zero with 0 order 2. So that's an example telling us this omega actually represents a special differential form or canonical divisor on this genus 2 complex curve, Riemann surface, with a double zero at the vertices of the polygon. Are there any questions about this example? But even in genus 2, you can have a different behavior for differentials. So let's consider another example here. So this time, so I take a decagon with 10 edges labeled by A, B, C, D, E into 5 pairs. Again, so I glue the pair of edges under the same labeling by translation. Okay. So now you can check that if you identify the vertices, they fall into 2 orbits. If you do this lower endpoint of A, it will become this point, and if you use this as upper endpoint B, it becomes this point, and then view it as the left endpoint of C, becomes this point, and this is the lower endpoint of D, becomes that point. This is the upper endpoint of E, and becomes this point. You come back. So these red points, and similarly for the other remaining 5 blue points, they actually form 2 different points even after gluing. And now if you count their respective angles, each of them will have angle 4 pi, again, which is an integer module of 2 pi. So 4 pi just means locally you will have, so 4 pi is 2 times 2 pi. According to our recipe, that means you have to glue 2 disks together. So that means omega locally will look like d of some coordinates w squared, where these 2 come from this multiple. And you differentiate, you'll get w dw, which tells us this differential form has a simple 0 at the blue point, and similarly as a red point. So in other words, this actually represents another kind of holomorphic differential 1 form, still on a genus 2 surface, which has 2 distinct simple zeros. So each simple zero under the nearby effect metric has angle 4 pi. So again, we can compute the Euler characteristic in this way. We have 2 minus 2g. Now we have 2 zero cells, the blue and the red dots, and 5 edges, A, B, C, D, E, and still 1 face in the interior of the polygon. So again, the genus is 2. So this is not a surprise because, so here our structure is more than the genus, even more than the complex structure. Even if you give me the fixed Riemann surface with a fixed genus and fixed complex structure, so in general, there is still a complex g-dimensional vector space of holomorphic differentials. So a general element will be a differential with distinct simple zeros, but the special ones where the zeros can merge to form higher order. So here we can have either a differential with a unique double zero, or we can have a differential with 2 simple zeros. So in many studies of geometric objects, so people like to put geometric objects with similar structures together to form a parameter space, usually called moduli space. So here, so let's fix the following data. So I'd like to consider a fixed tuple of positive integers denoted by m1 up to mn to mi. Each is a positive integer. So I consider their tuple denoted by this signature mu. So let's first create this set denoted by h mu as the modular space of flat surfaces, or equivalently holomorphic differentials of type mu, meaning if you want to consider them as flat surfaces, as polygons with parallel edges, then we want to make sure after gluing these polygons really have exactly n special points, and each point has a given angle given by this mi plus 1 times 2 pi. In other words, these n special points will become saddle points with a specified angle according to the given signature mu. And equivalently, if you want to use the more intrinsic definition of differential forms, then we can equivalently describe h mu as a modular space of holomorphic differentials of zero type mu, meaning it parameterizes such differential forms omega on genus G Riemann surfaces that have exactly n distinct zeros, where each zero has a Van order given by mi as an entry from the given signature mu. So I want to fix mu and consider such structures. And there's one condition you have to impose to make sure such space is not empty. So again, if you know Gauss-Bonnet, if you have a flat surface of genus G with n like conical singularities, you know the curvature around each singularity is given by this angle. You add them up. On the other hand, you have n punctured surface. You will have 2d minus 2 plus n equal to the sum of these mi. But this is also equivalently the degree of the cotangent bundle, canonical bundle on a Jins G complex curve, so that the associated canonical divisor of the one form, the zero order, must sum up to be 2d minus 2. So this is a condition we impose, make sure the space H mu is not empty. It's a necessary condition. From now on, I always consider this mu as a partition of 2d minus 2 satisfying this condition. For example, in the case of Jins 2, I've shown you two pictures corresponding to this mu equal to, here's 1, 1, just two simple zeros. And also here's mu equal to 2, just one double zero by zero, one shorter, and number of zeros. So in general, for a given genus, you still have finite many choices for any integral partition of 2d minus 2. Okay? But this definition so far only gives us H mu as a set. So what kind of space is it? When we say a space, we want it to have a geometric structure. So let's take a point, an element, just a Riemann surface X of Jins G together with a differential form omega of zero type given by M1 up to Mn. So I label the zeros as endpoints, Z1 up to Zn, on the surface X. Okay. I want to describe a local coordinate system on this modular space H. So what I'm going to do is first, I take this H lower one stands for the first homology of the surface X. But I want to consider an enlarged version of the relative homology by taking the positions of the n zeros into account. Let me draw a picture here. So topologically, when you have a Jins G surface, you can decompose it this way, and with some edge identification, you have some closed loops that generates the absolute homology H1 of X. And here we have gamma I for I from 1 to 2G. Because this group is of rank 2G, so these gamma I's are closed loops. There are some edge identification. But here, I also have special points given by the n zeros of differential form. Let's label them by Z1 up to Zn. So I consider open path joining each Zi, maybe to the last one, this one. Since the zeros are distinct, these are not absolute paths because they are not closed. So they are relative paths joining different zeros, but I just add them into the homology group. So that's what I wrote here as a relative homology. So how many additional paths do I need? Well, I just need, if I have n zeros, I have n minus 1 additional paths. These are labeled by this gamma 2g plus 1 up to gamma 2g plus n minus 1. I'm just choosing a basis, so these are not canonical choices. If you connect Z1 to Z2, that's also fine. But that will be redundant because you close a loop. So this closed cycle will be in the absolute homology. So I don't need it. I can represent this by these two relative paths. In other words, in order to choose a basis, this relative homology has precisely rank 2g plus n minus 1 via this additional n minus 1 coming from a basis of the path joining between the n distinct zeros. And if we have paths on the surface together with a differential form, the most natural thing you can do is to integrate. So I can integrate this differential form against a basis of this relative homology group. So I obtain 2g plus n minus 1 complex numbers. So this is a holomorphic form. These are like paths, so I can integrate. So these are called pure coordinates for this modular space. And if you believe these are, I'm going to explain why these are local coordinate, but if you believe these are local coordinate, as a consequence that tells us this modular space actually can be viewed as a complex manifold with dimension given by 2g plus and minus 1. That's what I wrote on the bottom line here. And the reason to believe these are actually local coordinates of this modular space is for the following reason. Let's go back to this picture. Now think of this polygon representation just as one point, one element parameterized in the modular space H mu. Okay, I want to deform it. The way how I deform it basically tells us how to see the local neighborhood. But how can I deform this structure? Well, I have to keep the parallel pattern. So all I need to do is I take V1, V2, V3, V4, just as 4 complex vectors. I perturb them a little bit. Maybe starting from this one, I can change each edges a little bit. I can make the polygon a little longer, a little thinner, and something like that. Right. And still in the same gluing patterns, it's V1, V1, V2, V2, and so on. And the resulting object remains to be an octagon. And if you glue the 4 pairs of edges, will still give you a genus 2 surface with a unique saddle point by identifying the 8 vertices. And this Vi, indeed, they're nothing but integrating dz against the underlying path. If I think of the underlying path is some path like gamma I on the surface, this Vi is just given by integrating of dz over the underlying path gamma I. And you may ask, okay, what about some other path if I draw like maybe connecting vertices in the interior by maybe cutting open the polygon? It doesn't really matter because I'm taking a basis. Any other options or path you give me will be a linear combination of these basis elements. If I know how to deform the basis, then I know how to deform any other element you give me. So in this sense, I think this is a heuristic but convincing argument to show you that deforming such structure amounts to deforming these edges, which are essentially governed by deforming these pure coordinates. Yeah, so this picture exactly was the one I was trying to explain here. So the edges are, in this case, they provide us local coordinates of the modular space parameterizing such object. We deform these edges that will change the shape of the polygon a little bit, but preserve the discrete invariant like genus, the number of zeros, and the angles. Are there any questions about this? So this object has a long history dating back to some interesting study in the sense of dynamics, but very simple to explain. So let me explain. So let's take the group of 2 by 2 real non-singular matrices, just GL2R. Okay? You view GL2R as an action of affine transformation, or linear transformation on the Euclidean plane up to translation. So if you take any matrix A, view it as a linear transformation, I can apply it to such a polygon. Okay? On the left, if I take each edge Vi, viewed it as a vector. So I apply A, this Ui just becomes the image of AI under A. Up to translation, because everything is defined up to translation. Okay. then if this V1 and the other V1, they are parallel vectors up to translation, clearly their images U1, U1 will still be the same pair of parallel vectors that can be identified by translation. So I do the same thing for all the pairs of edges. The resulting object still lives in the same modular space, meaning the number of saddle points, like special vertices, and the edge identification remains to be the same. So this action is really on each modular space of different forms of a given zero-type mu, or on each modular space of flex surfaces with a given number of saddle points and given angles. Okay, it preserves such structure. So it's a very simple action. And this action sometimes refers to Teichmüller dynamics, has something to do with surface dynamics and Teichmüller theory. One leading question in the study of Teichmüller dynamics is to study the behavior of such orbits under this GL2 action. In particular, it studies the orbit closures in the modular space H mu, because I just told you this H mu is a complex manifold. It has topology, a complex structure. I have something going inside it. Take a point, x omega applies the GL2R. It goes around, sometimes maybe ergodically, sometimes you may wonder maybe the orbit forms a special subset. Even if you take the closure could be much smaller than the total space. And how to study the behavior of such orbits. For example, let me draw the picture, just view this as h mu. I have a point x omega here as the object parameters here. I run this GL2R, look at the orbit. Maybe you may expect this orbit goes ergodically and it takes a closure, you get total space. Or maybe sometimes you get a special point x omega to start with, and you run the orbit might be something much smaller, even if you take closure, it's not the total space. We don't know yet, okay, just by looking at this definition. I'll show you some known results soon. But why this study can be hard? Well, there's a one delicate point when you look at the polygonal model of differentials. So let's look at this very simple picture. A flat torus given by the unit square. Okay, I identify A, B, B, just get flat torus. Okay? However, let's apply this GL2 action by this matrix 1, 1, 0, 1, like a shear transformation horizontally to the right. Okay? I get this square becomes the following parallelogram. Now I cut it open and reglue, because everything is defined up to cut and paste under translation. So I move this right triangle to the left by identifying this B with the other B. Then suddenly, the resulting object returns to be the same as the starting object, although the middle one looks very different. So what's going on is that, in general, if I give you a flex surface like this, which looks maybe like of regular shape, it's possible that you can cut it into many pieces and resemble in a different way under translation, so that the new presentation of the polygon looks much longer and thinner. But still, they represent the same element up to isomorphism. So the polygons can cheat us. There's no canonical way to represent a different form by using polygons. You can represent in certain ways, but up to cut and paste and translation, there are many ways to do it. So we cannot just say that these two polygons look so different, then they are different. Maybe they are very close, maybe even essentially the same in the modular space. That's one of the reasons why when we study this GL2R action just by looking at polygons is not enough. It's a little misleading. Okay? So there have been a lot of studies to classify special GL2 orbit closures, in the sense that when the closure is not the entire space. So there are a lot of work. I can't even mention all the names here, but the punchline is that a complete classification of special orbit closures is still missing. So we don't know yet. We have a lot of partial result, especially in low genus, but in general, it's still open. It's coming next. Yeah. Yeah, but that's not a complete classification, it's rather a structural result. You're right. So I won't let you down. Let's do it. Is that asking Mr. Honey? However, as Yihua just pointed out, there's one, maybe the most important result in this field, maybe in the last 10, 20 years, due to asking Mr. Honey and also another paper with Mohammadi. Although they don't classify completely special orbit closures, they give us like sort of like a study for their DNA. It tells us how they should look like. The result is as follows. You take the closure of any such orbit in this modular space H mu. So you may wonder, so how the closure sometimes can be as bad as maybe, I don't know, counter set or Julia set, and can it be something better, like a manifold, like submanifold, subvarieties? So their result actually is even stronger. They said the closures of any such orbit, they are always locally linear in the sense that locally my modular space has these pure coordinates, right? So I have local coordinates. Now I have a subset locally coming from this orbit closure as a subset. I want to describe defining equations, if possible, by using these local coordinates. What kind of equation can define the Riemann locus or define this subset coming from an orbit closure? Their result says that this defining equation for this orbit closure, they are always real linear equations of the ambient pure coordinates. If you think of locally this as a vector space with coordinates given by pures, then this orbit closure is always locally linear subspace, where the defining equations are having real coefficients. Okay? And as I already wrote here, this is an important part of Mr. Harney's field meta work and also an important part of Eskin's breakthrough prize. And soon after their work, Simeon Philip, who were here last week at ICBS, and he strengthened their result by replacing this term real. Well, real number can still be transcendental, pi, e, right? So if you have transcendental numbers, it's hard to do something more algebraic, like geometry. However, Simeon Philip shows that you can strengthen by changing this real number to be algebraic numbers. In other words, defining equation could be something like square root of 2 times v1 minus maybe square root of 5 times v2 equal to 0. But it cannot be something like a pi or e involved. Okay. So Simeon Philip's result actually reveals a deep, maybe a deeper connection from this seemingly analytic and dynamical point of view to something more arithmetic. In other words, all these orbit closures, they are defined over a number field. They are defined over Q bar. They are algebraic varieties.
Are there infinitely many examples where the degree of the field is bigger than 2?
Maybe in low genus, I have to check the reference in genus 3. Yeah, maybe for Teichmüller curves in genus arithmetic, sorry, not primitive Teichmüller curves in genus 3.
I think it's finite.
For Teichmüller curves, I'm not sure. I think there are some condition on the rank of such orbit closures. Yeah. But let me also take this moment to, before I move on, to try to promote, to highlight this field, especially for people working here. So I think this is a fascinating subject, and there are only few, as far as I know, people working here, like Zhang Yuhua from Tsinghua and my other collaborator, Guilam Tahar, they're working here in Binsang, and also Yu Fei from Zhejiang University. I do hope so in the near future, this field can, and this group can grow bigger and make further bigger impact on this fascinating topic. So next, I'm switching to some of my own work and more from the viewpoint of combined with algebraic geometry. So I grew up as an algebraic geometry. So one thing I'd like to say is that, so in algebraic geometry, when you study such objects, one important technique or viewpoint is how such objects degenerate. So that is equivalent to say that how do we compactify this modular space H mu? Right? Clearly, it's not compact. Right? So the underlying Riemann surface, you can pinch some curve to make it singular. And if I fix the zero type, if I let two zeros arbitrarily close to each other, the zero type can change. That means I cannot preserve the same type mu. So these are two behaviors of degeneration. So let me show you something even more strange. I have it on my slide, but let me first draw it on the blackboard. So I'll show you the answer. So suppose I take a flat torus, right? Okay, let's take a very big flat torus. I remove from this flat torus, from its interior, I remove a smaller flat torus. Yeah, let's draw it this way. Okay, so let's have another parallelogram with two pairs of parallel edges. I remove it. I look at the complement. Okay, it's a strange drawing. Nevertheless, you can check that this actually represents a genus 2 surface if you do the edge identification. It is still an octagon with 8 edges. 1, 2, 3, 4, 5, 6, 7, 8. Not that different from the previous octagon I showed you. And here's one special point, still like a saddle point. Not on the outside vertices, because these 4 points, if you glue them together, still give you the angle 2 pi. It's not special. If you look at the inner vertices, these 4 points. But now, since I look at their complement, I have to count the angle outward. I have to add up these 4 angles together. That adds up to 6 pi. It gives us a saddle point, which is a double zero for the corresponding differential form. So it's really the same example presented in a different way. So now I want to degenerate it in the following sense. So I want to shrink the small torus that I removed to make it arbitrarily small. To shrink it. Let's call this removed torus Z, outside torus Y. Shrink Z. Okay. And in the end, it just shrinks to a point. You just remove point. So the Y remains the same. Z degenerates to a point. You get a punctured or marked torus. And it's a little funny, right? Because here you have genus 2. This one becomes genus 1. Okay. It might be okay to some of you, but if you really do the kind of geometries or complication of modular spaces, you don't like the genus to jump. Right? You want to keep the same genus. So where is the missing one genus? Where does it go? You think about it, well, you really think about it, well, until you realize the following picture. So what I showed you on the blackboard was only the upper half of the answer. Conversely, if you consider everything in a relative point of view, if something becomes arbitrarily small, it might not be that thing becoming small, it just becomes maybe some other thing become arbitrarily large. So for example, if you stand inside the removed torus Z, you might not realize it is shrinking, but the outside world is expanding to arbitrarily large. So now you look at the lower half picture, you keep the size of the removed torus Z, but let the outside torus Y to explode to be arbitrarily large. How large? Just to be the entire Euclidean plane. Then you get this picture. In a sense, it is still on a flat surface of infinite area. That really means whenever you have infinite area flat surface, you will see not a holomorphic differential. At infinity, you will have a pole which correspond to a meromorphic differential. So topologically, in this picture, if you add a point at infinity, still do the edge identification. You can check topologically this remains to be a torus. And actually, this represents a meromorphic differential with a double zero, still as the blue points, and a double pole at infinity. And now you take the two tori together, that recovers total genus 2. So topologically, you have to glue this point with the infinity of the other torus that disappear. And this is kind of the idea. So I used with my collaborators, Bainbridge, Gendron, Grushevsky, Muller. So we described a certain complication of this modular space H mu that are denoted by this PH bar. So I consider everything modulo C star just because scaling a different form doesn't really change the underlying surface and doesn't change the zero type. But this relative scaling gives us a way to describe this complication, which is useful for many, many purposes. And in short, an object in the boundary of this complication just parameterizes possibly meromorphic differentials on subsurfaces of the degenerate Riemann surface. So the Riemann surface itself can become reducible, like in this case. You have two tori glued at one point. On each torus, it carries their differential. Sometimes it becomes meromorphic, just meaning the other part of the surface looks much, much bigger to it. So it looks like a pole. So the degenerate part of the surface will see a pole corresponding to a meromorphic differential. It's a technical point, but I think the picture is enough to give you an idea. So I will only use this complication at the very end of my talk. So for now, let's know this complication exists. That's enough. Okay. So let me move to the last topic of my talk about geodesics on flat surfaces. You may have played like billiards on a regular rectangular billiard table, but have you ever played on an L-shaped billiard table? Right? Now suppose you take this L-shaped billiard table, you look at the billiard trajectory. And that sometimes can be studied by using geodesics on a flat surface. So how do I do that? You can take this L-shaped billiard table, right? Suppose I take a billiard ball and hit it this way. Okay. When I hit it here, although it reflects, I may want to reflect the surface instead, right? I just reflect the surface instead. And let it continue sometimes, and hit it here, and then consider this edge, glue with that edge, and go back. And then in a sense, this is similarly to the study of geodesic on a closed surface, like in the bottom picture. And you may have many different ways of counting different objects. So here, I'd like to count so-called saddle connections, meaning, so saddle points are those special points or zeros of different form. A saddle connection is just a real straight line, a real geodesic, drawn in two saddle points. So one toy example is consider a marked flat torus like this. Okay? And I mark the vertices of the torus, just pretend to be a special point. Okay? And suppose I want to count saddle connection just from this point to itself. For example, if I do this direction, here's the middle point, it will go down and then go here, right? But I can also unfold this torus into the universal cover that is the entire plane, so that these vertices become integral lattice points in the plane. And suppose I want to count the number of saddle connections of length bounded by some large number L. Okay. So it might not be easy to get a precise count, but at least we can control its asymptotic behavior. So in this picture, it's clear that if I unfold this torus so that the vertices become lattice point in the plane, so if I count a saddle connection of length bounded by L, what I can do is just draw a large disk of radius given by L. I just enumerate the number of lattice points inside the disk. But that's, roughly speaking, is approximated by the area of the disk, which is pi L squared, with some lower error term that tells us this content at least has a quadratic growth rate given by L squared times sub pi factor. So modulo this pi factor, the leading coefficient is always called the sigma of H constant for such counting problems. Okay, so that's a kind of phenomenon I'd like to highlight, this quadratic growth for some bounded object like stellar connections, and then you want to analyze the leading coefficient. That coefficient is called sigma of H constant for this counting problem. And here I'd like to consider a special type of sigma of H constant called area sigma of H constant. So roughly speaking, so sometimes you may have not quite a stellar connection, but you may have, suppose my flex surface look like the following. And maybe in the middle of the surface, I have this edge and that edge glued together by translation. So I can have a closed geodesic without containing any saddle point that moves parallelly in the same homology class to fill the cylinder until it hits some saddle point here and there, and I stop. Okay, if these two edges are identified and you wrap up, you get a cylinder. I'd like to consider the counting for such cylinder objects and taking the area of the cylinder into account as a special parameter, as a weight. Sometimes, as you know, if you count an object, you do not always count one. Sometimes you have to take some extra information to make the counting more meaningful. So here I take the area of the cylinder into account. But the area of the cylinder is easy to compute. I have a width curve given by W, I have a height given by H, so the area of the cylinder is just height times width. It's given by the area of this parallelogram. Okay, as I wrote here. And here's some global examples. I have a flex surface. If I consider in the horizontal direction of a bottom cylinder of height 1 and length 4, and I have a top horizontal cylinder, the width curve is 1, the height is also 1. I have two cylinders of different areas. And if you go on different direction, you might find other cylinders, okay? And I want to also take their areas into account. And for all such countings, we have the following behavior. So here, so X is a given flex surface. Let's uniformize its area to be 1. So I take a large enough number L to bound what? So this is a little small, let me read it for you. To bound the width of the cylinder. I want, so this width, this W thing, to be bounded by a given number L. So for L large enough, I may still have many such cylinders. I just take the sum for all such cylinders on the flex surface X, where the width of the cylinder is bounded by this large number L. I sum up their areas together. This sum is called N, which depends on L. Okay. And Veitch and Eskimizer, they showed independently that for any orbit closures, so you actually can find a constant C where this number has a quadratic growth rate, roughly given by C times pi L squared. That we have seen this behavior for counting saddle connection on the flat torus. The same asymptotic still holds for such a counting problem in higher genus in general. And this number C, defined this way, is called the area sigma of H constant of the orbit closure. If you change X and get a different orbit closure, this value can also vary. So it depends on the geometry of the flex surface as well. Okay? But if two flex surfaces give you the same orbit closure, I think their sigma of H constant are the same. So it only depends on orbit closure. It has a generic behavior with respect to the closure of these two orbits. So here's a result I did a few years ago with Martin Müller, Adrian Sauvagy, and Don Zaghi. And we actually computed this number for the biggest orbit closure, the total space H mu. So I'm saying you take any general flex surface in the modular space H mu, where the orbit closure is the total space. Okay. Then this area Zigovich number surprisingly can be represented by, it looks like a complete formula, but this formula is really occurs in the cohomology ring of the compactified modular space. So here, this pH bar is a complication I told you earlier. If I want to do intersection calculation in the cohomology ring, I need the underlying space to be compact. Like in the affine plane, two lines may suddenly become parallel, don't have their intersection. But if you project ones to be a projected plane, any two lines will intersect at one point. So here's the same thing. I have a compactified modular space, okay? And then I have some so-called cohomology classes. Each is a divisor class, like in H upper 2, the real codimension 2, or complex codimension 1, like hyperplanes, complex hyperplanes, in the modular space. So I won't say too much about the meaning, but let me say that if you know the psi classes, well, Witten's conjecture, conservative theorem, I have Riemann surfaces with the zeros as special points. So for each zero, I can view it as a mark point and look at the associated psi classes. So those are the psi classes coming from the cotangent lines of the mark points coming from the zeros of general form. And there's an additional class eta coming from the projectization. Because here, originally my modular space looked like locally like a vector space, right? My differential form omega can rescale by any C star. If I project wise, like a project space that carries a hyperplane class O1 or O minus 1, that is my eta class, which is also a divisor class. And you do this calculation, we have this ratio. So there's a one last divisor class delta coming from the total boundary of this modular space, parameterizing degenerate objects where the underlying Riemann surfaces become nodal surfaces, become singular. It's similar to the holomorphic boundary. And the top actually governs how this cylinder degenerate when you pinch the core curve. So you can see when you pinch the core curve of the cylinder, it will lead to some nodal singularity. So that's why this boundary parameterizing nodal surfaces appear. The denominator has a significant meaning as well. So I won't highlight here, but in short, the denominator is responsible for the so-called Mezevich volume of this modular space. Yeah, there was another talk by Anton Zorich last week regarding the Mezevich volume, which can be computed by some intersecting number like this on the bottom. So this formula actually has a meaning, right? On top, you have some behavior related to shrinking the core curve of the cylinder, go to the boundary of the modular space. You then average it down by dividing the total volume of the modular space. So I think at least it makes sense, right? I hope the structure of the formula makes sense. So in the last 2 or 3 minutes, so here I said, so why do I want to count the area of the cylinder? Because if you write down the area of the cylinder, that is H times W, right? And originally, our counting problem, we have to divide it by this L square. L controls the length or the width of the cylinder, right? If you take this L square into account, so this just becomes H over W, the height over width, as area over W square. And now you take a cylinder, you pinch the core curve of width W, and topologically you get a node, right? So this object is responsible for this delta C as a degenerate object. But we don't always count it as one node. When you have intersection, maybe the two things are tangent, maybe there's a higher intersecting multiplicity. That intersecting local behavior is encoded by this cylinder modulus H over W that tells us the local behavior of how these intersecting numbers work. So that's a technical detail. So in the last slide, let me just show you one iterative application. So about 20 years ago, by computer experiments, asking Zorich conjectured that if you look at such area Zigovich constant for the entire modular space H mu, they uniformly approach the number 1/2 when genus goes to infinity, regardless of the zero type mu, it doesn't matter. And Amon Agavo, who was also here with Anton Zarich, both were here last week, he proved it by using an amazing commutator argument. And about the same time, so by using our intersection formula with my collaborators and an earlier paper to deal with when mu contains simple zeros only, in a later paper we did it in general, we can analyze the behavior of those intersection numbers and do some recursion about the genus of mu to give, indeed, not only this 1/2, and also you can expand it into lower degree terms. I can see some lower degree term related to some power of g on the bottom. Okay, I think my time is up. Let me stop here. Thank you.
Thank you for the wonderful talk. Any questions?
Okay. How do you deal with normalization? Like, you get this nice formula in the previous slide for the when you have the psi class, right? Does it matter how you normalize Mason-Beach volume?
It matters if I only wanted to compute the volume. It matters.
Mm-hmm.
Look, but here I have a ratio.
But they're of different dimension.
No, they cancel out, right?
Okay.
What do you mean by different dimension?
Well, one is on the bound. You have a delta. It depends on how these objects are defined.
Yeah, but here I also have the two numbers differ by 1. Right? So this object has complex dimension precisely 2g minus 2 plus n. I have 2g minus 2, and I have n minus 1, and 1 altogether. I have 2g, also plus 2 minus n.
So what is the 4 pi squared?
Oh, that just comes from the Ziegler-Witch constant normalization. It's always there, depending on how you normalize the leading coefficients. Yeah, that's a convention. Yeah, maybe it comes from, that doesn't matter, but once you fix this one, because the Ziegler-Witch constant is the leading coefficient of L squared, something like that, right? But the leading coefficient will have some pi factor. Sometimes people might normalize by pi, sometimes by pi squared, sometimes by some 4 pi squared. You choose a normalization so you can work out the remaining thing.
More questions?
Hello, thank you for your talk. Is there some analog result about asymptotics of Ziegler-Witch constant for arbitrary orbit closures?
Yeah, that's a wonderful question. So I talk about orbit closures as a main object to study. So here, let me make it clear again. So this C mu is only for the total space. In other words, for the general flat surface whose orbit closure is a total space, is ergodic. But as I already mentioned, you can have a special one form containing H mu whose orbit closure is much smaller. It could be a proper linear subspace. For those, we conjecturally have a similar formula. And we can prove it with Martin Muller and Alice Guhart and also Adrian Savages for different cases. The conjectural formula is written in a paper. Basically, it takes a similar form. You should replace this eta and the power of eta by using the dimension of the rank of the absolute pairs that defines the orbit closure. And these additional set classes come from the rank of the remaining strictly relative pairs. And the delta is still the boundary of the orbit closure. And then that formula actually I think should work uniformly, and for many cases we checked. Yeah, so far we can prove it for the so-called orbit closures with absolute pairs only when there's no set classes. But in general, I have the conjecture formula like this, but the whole proof for most general cases is still open.
Because of the time limit, let's send the speaker again.
Thank you.